if you do 32 bits, it's going to be like 12 times as slow, because just like splits it all on 8-bit operations. So that's something you have to take care of if you have a counter, for example. Just knowing that if you have a 32-bit counter and compare it, you're just going to have a much slower and bigger code. So you can use floats as well. I wouldn't advise to do that, because it's... but well, what you can do is basically to see where all the speed issues come from is to use a profiler. So it's actually pretty easy to build a profiler on the atmel. What you do is you just look on the stack frame with a pointer, look where the calling address is from, and send it over to the host at a regular interval. And you can just basically interpret it on the host with some, I think it's called add to line, which takes an address and gives you the code line in the source code, and then you do some kind of plotting of that with a Perl script. So it's actually pretty easy to build. It's like 20 lines of code. It sends it over the MIDI platform. It has a bit of a performance impact, but it's actually pretty cool to see how much time is spent running in the big run loop, or if you see that like 80% of the time is spent in the UART code, you know, okay, maybe I should revise how my UART works. And the whole code for the profile, it's basically pretty portable, and you can look it up in the Git as well. But the biggest issue in the whole embedded programming is basically code size. I have 64 kilobytes of code size, and the newest firmwares are like 60 kilobyte big. One major reason for that is C++, actually. It does a lot of pointer arithmetic because the whole class information is stored in a structure, so it's always looking up the pointer to the class and then doing some indirect addressing to get the member variables. When you call virtual pointers, you have the same kind of double lookup that happens, and that adds a lot of pointer arithmetic. And GCC is not very clever using the extended registers of the AVR. So basically, most of the time, you just like reload stuff from the frame pointer, does some 16-bit addition and subtraction and multiplication, and it just like bloats your code a lot. That's, I think, because most of the optimization for GCC are not aware that you're running on an 8-bit CPU, so it may be that there's some kind of stuff happening there. So basically, you have to be pretty careful when you use arrays of objects, for example, to organize the accesses so that it doesn't do a big bloat. Using intermediary pointers works pretty well, for example. Another big issue is when you use templates, you have a lot of code duplication taking place that the linker doesn't recognize. So, for example, if you have a ring buffer of a pointer to an 8-bit value and a ring buffer with a pointer to a 16-bit value, is actually exactly the same assembler code, but it just generates it twice and links it twice into it. So you have to be careful when you use templates and data structures and lots of different specialized data structures. It's just going to be duplicating stuff all over. And a big gripe I have with G++ is that it just doesn't optimize my static constructors. Like, I'm not using any dynamic memory allocation, and it just generates a new constructor for every object I instantiate and just links it in with static values that just copied into memory, and that's it. So I think on my new firmwares, it's like 60 kilobytes of code, and then about 40 kilobytes of that are just static constructors. So it's pretty horrible. A big hope I have is that LLVM is going to be working on the 8-bit CPU pretty quickly on the AVR. There's a port going on, so if you want to contribute, and it basically shrinks the whole code at link time and just rips out all the whole constructor stuff. And my first tests were like 60 kilobyte with GCC and 12 kilobytes with LLVM. In the article in the proceedings, I have a whole part about compiler flags optimization. That's the easiest way to get some bytes out of it, but it's a bit trial and error. What's very important to actually do some kind of sensible optimization is look at the output of the compiler. Like, the compiler does a lot of stuff wrong sometimes, and you need to be able to read the assembly. Not maybe write the assembly, but being able to see how it resolves member lookups, for example. You can plot sizes with a lot of the toolchain utilities, which I talk about in the article as well. And what you need to do as well is maybe to understand how C++ works when it's compiled is just build a lot of dummy programs and look at the assembly output and then try some stuff to see how the assembly output changes and see basically how G++ interacts with it. And it changes with every GCC release as well, so you need to do it over and over. And actually, this knowledge of being able to read assembler programs, maybe write some of them, turns out to be really useful later on when you're debugging stuff. I'm going to talk a bit about refactoring for code size. A few of the tricks is basically avoid big switch statements. That's like the worst thing ever. And if you have a big switch statement, just use a function pointer lookup table, for example, with different states. What's very useful as well is when you have big parsers, which I have, for example, for synthesizer dumps, like the settings dump. I have these huge parsers. It's much easier to build stream parsers that just take one token at a time because you avoid having the need for a big buffer of a few kilobytes in RAM, so you can just basically parse the stream as it comes in. That's a huge space saver as well. What I mentioned already is reorganizing array loops. If you have like indirect addressing taking place, just using temporary pointers to tell the compiler, no, I need this value, just please store it in the register, instead of computing it all over. And a lot of those tricks are available in a book that's freely available online called Small Memory Software, which has a lot of patterns about how to shrink specific cases, how to design your software for a small memory, both code memory and data memory. So that was the part basically about optimizations. There's a lot of details involved. And I mean, if you want the smallest code size, maybe the best idea is just like to use the next bigger processor if you can handle it price-wise. I don't think there's not much need for completely writing an assembly anymore. A few people still flame me on mailing lists for that. So that was the part on optimization. Are you following from the technical kind of stuff, or am I too quick? Because this is going to be quite technical as well, which is timing and latency. And I'm building these MIDI controllers, which doesn't sound like a big issue at first, but it's actually one of the hardest real-time requirements I had. Like, for example, if you want to trigger a bass drum that's supposed to be sounding at exactly the same time as another bass drum, like basically every microsecond is going to make a difference in the sound that comes out because the sound can phase. So even like small shifts, you hear them pretty well. It's not like they're big. They're bad on a timing point of view, but the ear is so precise that you can actually hear stuff phasing and hear stuff that's out of sync pretty easily. So it's actually turned out to be a pretty big issue, is the whole real-time part of music that you need to have low latency when I press a button and a sound is triggered, for example. The second biggest issue, which happens a lot in music, like especially with MIDI and synthesizers, is that you synchronize multiple devices together so they run in the same sync, and then you start to have problems keeping up with the counter, so you're always at the same bar. Like you couldn't be in sync, but then just out of phase. That can happen pretty quickly if you're not careful. And the biggest issue is actually synchronizing. So one of the possibilities is just to take incoming clock messages, which are like a metronome, running pretty quickly, giving me the sync, and just react on every incoming clock event. But then I have like latency problems. I need to react on it immediately, and depending on the code that's triggered by this timing event, I can just have like note messages coming out of it that just like phase around. But it's very easy to do, just like basing on every incoming clock message, you trigger a clock event. What you can do as well is use a phase lock loop, where you have your own timer running internally, and it adjusts its frequency and its phase to the incoming clock. And then even if you have jitter on the incoming clock, you can filter it out. Or what you can do as well is just like pull the synchronization around, so that if you have like a synthesizer has a bigger audio buffer and a synthesizer has a smaller audio buffer, you can filter it out by delaying or actually playing the clock in the future. I don't know if that's very clear, but you can basically phase out your own clock, which is pretty useful if you start to change devices. So, but that's when the really horrible stuff starts to happen with the phase lock loop. You need to have a pretty quick timer to be able to cover the whole range of MIDI tempos, which goes from like 20 BPM to 300 BPM, which is actually an order of magnitude bigger. And it turns out you run pretty quickly into numerical problems because you're using integer values, 32-bit integer values, for example.